All right, let's talk about a toolbox, but not one with hammers and screwdrivers. This one holds two of the most extreme things in the entire universe: lasers with almost unimaginable power, and the fourth state of matter itself, plasma.
I mean, how do you do all that? It sounds like something straight out of a movie, right? But these aren't just crazy what-if scenarios. These are the kinds of questions scientists are tackling right now, using a technology that combines unbelievable power with a medium that's pretty much indestructible. And that partnership, that's the secret sauce. It's the incredible relationship between the focused energy of these ultra-intense lasers and the unique resilience of plasma. So let's break down what makes this team up so incredibly powerful. Okay, so to really get this, we need to look at the two partners individually. And we're going to start with plasma, which is kind of the unsung hero of the high-energy world.
You know about solids, liquids, and gases. Well, plasma is what happens when you just keep cranking up the heat. It's matter that's been heated so intensely that electrons literally get ripped away from their atoms, creating this sort of superheated, charged soup. Now, here's the magic trick. It's basically unbreakable. You can hit it with insane amounts of energy and it just takes it. It won't shatter or fall apart.
Now let's meet the other half of this power couple, the laser. And listen, we are not talking about your keychain laser pointer here. These are femtosecond lasers. Their pulses are so short, we're talking millions of a billionth of a second, that they can pack a petawatt of power. That's a quadrillion watts. For that tiny, tiny instant, a single one of these beams is more powerful than the entire electrical grid of planet Earth. Just think about that. So, here's where it all comes together. You've got a laser so powerful it can strip all 92 electrons off a uranium atom, creating this crazy dense, high-energy environment. And then you have plasma, the only state of matter that can actually handle that kind of abuse without just, disappearing. The laser is the hammer, and the plasma is the anvil. All right, so we've got our ultimate hammer and anvil. So what's the first thing we can do with this toolkit? Well, how about sculpting materials with light in ways that were totally impossible until now? This incredibly intense, focused energy from the laser hitting the plasma gives us a level of control we've just never had before. We can etch, we can carve, we can even create materials with features that are smaller than the wavelength of light itself. And just look at the scale we're talking about here. It's mind-boggling. This technique, called LIPS, uses the laser to etch these superfine patterns onto a surface like quartz. We're talking structures just 150 nanometers wide. For perspective, a single human hair is about 80,000 nanometers. This kind of precision opens up a whole new world for creating materials with brand new properties, like, say, self-cleaning surfaces or way more efficient solar cells.
But okay, carving surfaces is one thing. We can go even further. By blasting a target with one of these lasers, you can instantly vaporize the material into a plasma plume, which then cools down and condenses into totally new forms of matter, like nanoparticles.
And the crazy part is how precisely we can control this. For example, if you fire the laser at a target made of aluminum, you get a cloud of these tiny nanoparticles that are all consistently between 10 and 50 nanometers. It's like a factory on a nanoscale. This whole toolkit isn't just about building stuff. It's also about seeing stuff. That same laser-plasma interaction is actually one of the best ways to create really brilliant short-pulsed X-rays. This basically gives us a super powerful camera for high-resolution imaging of everything, from medical scans to analyzing new materials. Okay, so we've gone from the microscopic world of nanoparticles. Now let's zoom all the way out to probably the most ambitious engineering project humans have ever attempted, creating a miniature star right here on Earth. Yep, we're talking about inertial fusion energy. This is the big one. This is the holy grail of energy research. The goal here is to replicate the very process that powers our sun, nuclear fusion, to create clean, safe, and practically limitless energy for the entire planet. And you guessed it, the laser-plasma interaction is at the absolute heart of this whole quest.
So how on earth does it work? Well, it all happens in 4 ridiculously fast steps. First, the laser strike. Hundreds of powerful lasers all fire at once, blasting a tiny fuel pellet from every direction. Then, implosion. The surface of that pellet instantly vaporizes, creating this immense rocket-like pressure that crushes the pellet inwards. Next, compression. The fuel inside gets squeezed to densities even greater than the core of the sun. And finally, ignition. The atoms in the core fuse together, releasing a massive burst of energy. And listen, this isn't some brand new idea. Scientists have been on this quest for decades, building bigger and badder lasers to get the job done. We've gone from about 100 joules of energy back in the 70s to megajoules today at facilities like the National Ignition Facility. And the next generation of lasers? They're being designed right now to power the very first fusion plants.
Of course, you need the right fuel for the fire. This table shows a few of the options. Now you can see the DT reaction there, which combines two isotopes of hydrogen, deuterium and tritium. Now look at its energy output, 17.6 million electron volts. That's a huge difference compared to the others, and that's exactly why DT is the frontrunner right now. It just gives you the most bang for your buck, making it the easiest path to ignition.
But, and this is a big but, there's a huge catch. That implosion has to be perfectly symmetrical. I want you to imagine trying to squeeze a water balloon in your hands to make it a perfect tiny sphere. What happens? If you squeeze just a little unevenly, parts of it bulge out, right? Well, that's basically the Rayleigh-Taylor instability. If the laser compression isn't absolutely perfect, the fuel just kind of squirts out instead of fusing. Getting this right is one of the single biggest hurdles in all of fusion research.
Okay, so far we've used our toolbox to build things, to sculpt things, to manipulate matter. But now we're going to turn it on something even more fundamental. Now we're going to probe the nature of empty space itself.
It's a pretty wild question, isn't it? What happens when you take this unbelievable concentration of energy, this laser beam that can tear atoms apart, and you focus it on a perfect vacuum? What could possibly happen? Well, the answer changes our whole definition of nothing.
It turns out that according to a theory called Quantum Electrodynamics, or QED, the vacuum of space isn't really empty at all. You can think of it more like a simmering sea of virtual particles that are constantly popping into existence and then vanishing again almost instantly. We're talking pairs of particles, like an electron and its antimatter twin, a positron, all doing this constant quantum dance. So a laser this powerful is actually strong enough to disturb this quantum foam. It can literally shake the vacuum, which lets physicists test some of the most profound and mind-bending ideas in all of science. They're asking things like, can we shake it hard enough to turn those virtual particles into real ones, creating matter from nothing but light? Could we force empty space to act like a crystal that bends light in strange ways? Could we even find new exotic particles like axions hiding in there? These are the questions at the absolute frontier of what we know. So just think about the journey we've been on. We went from etching microscopic circuits to forging miniature stars for clean energy, all the way to questioning the very nature of empty space. This incredible partnership between lasers and plasma is a fundamental tool that works at every single scale of the universe. The only question left is, what are we going to build with it tomorrow?